Hey folks, in this lesson we're going to compare two means. In the previous section we compared two proportions, that'd be p hat. The only difference comparing two proportions and two means is with, when we're comparing two means, again you're going to see mu or x bar. You can use a t-star value and a t-distribution table instead of a z-star or a z-score and a z-distribution table. That's the only difference. So remember with t-star values you have degrees of freedom, and that degree of freedom is n minus 1. All right, so let's get to it. Oh, also, we only really use comparing two means if you want to compare like two product performance. Maybe you want to compare whether or not Coke has more sugar in it than Pepsi, or maybe you want to compare one brand of jacket is better than another brand of jacket as far as how well it keeps you warm. So we're comparing two different products, things like that. So basically, in the previous example, we talked about two proportions, and now we're going to talk about two means. So this example deals with comparing polyester. So basically, we want to compare how well polyester holds up in a landfill, or how fast it decays. So the question says, how quickly do synthetic fabrics such as polyester decay in landfills? A researcher buried polyester strips in soil of different lengths of time, then dug up the strips and measured the force required to break them down. Breaking strength is easy to measure and is a good indicator of decay. Lower strength means the fabric has decayed. The researcher buried 10 strips of polyester fabric in a well-drained soil in the summer. The strips were randomly assigned to two groups. 5 of them were buried for 2 weeks, and the other 5 were buried for 16 weeks. Here's a breakdown of the strengths in pounds. Here we are. Here's group 1, and this is on the strengths level. And here's group 2, who stayed for 16 weeks. Here's their strength level. And then it says, do the data give convincing evidence that polyester decays more in 16 weeks than in 2 weeks? So they created this plot for us. They basically made like it's called a phantom plot, but basically comparing two dot plots above each other. Here's one dot plot, here's the other dot plot. Take a minute to look at that and see if you can make any assumptions about what's happening with the strength level when we compare these two dot plots. Again, pause the video and then take a minute and see if you can figure out if one looks like it's stronger than the other. All right, hopefully pause the video. You should notice that in this group 2, it looks like most of their values are lower than the bulk of these, like it's 3 above bulk of their values. You got one here that look like it's way higher than all the others, but most of the data, all but one of them, are below the majority of the group 1's value. So it looks like these have a weaker strength, all right, breaking strength, just by looking at that data. Also, looking at this, take a minute, let's take a calculator, and I can actually calculate these means here. So I'm typing them in, 118. I'll type them in on my own. So I have them typed in. I can calculate those pretty quickly by hand, but I trust technology to do it well. So stat, calculate one variable statistics for list 1. Looks like the mean for the first set is 123.8, and look like the standard deviation of that sample is about 4.1. Look at the second set. Look like the mean is about 116.4, and the standard deviation is about 14.39. There's no difference. The mean 1 minus the mean 2 would be 0, or x bar 1 minus x bar 2 would be 0. But in this case, x bar 1 is 123.8, x bar 2 is 116.4, and that difference is not 0. That difference is about 7.4. So there's definitely a difference in how well the polyester stands up to time when it's buried in landfill. I can see that mean is not centered at 0. That mean is centered someplace above 0, someplace over here. That's all we'll do with that example for now. Going to the second example. The sample distribution of the difference between two means. And this time we're comparing girls' heights. So take a minute to read this example. It's coming from textbook on page 636. Take a minute to read through it now. So from the survey, you should have gotten that they're comparing the heights between 10-year-old girls and 10-year-old boys. And they got a sample of both groups. And it looked like the 10-year-old girls, are females, has a mean height centered around 56 point something, slightly bigger than 56. And then 10-year-old boys have a mean height centered someplace lower. And the difference of those means is higher than 0. Notice 0 is here, and it's someplace higher than 0 for the difference of those means. What we learned in chapter 7 was that we saw that with sample distributions of sample means has the following characteristics. Shape. If the population is normal, then a sample distribution of X bar will also have a population that is normal. And the second thing you noticed was if the population isn't normal, the sampling distribution of X bar is approximately normal only if it's large enough. Say n is greater than 30, greater than or equal to 30. And that's according to the central limit theorem. So that's what we already know. So if we took a sample from a normal population, that sample should also be normal. If it wasn't normal, we need 30 plus of a random sample for it to actually look normal. We also learned that the center for the sample should be also about the same as the center for the whole population. We also learned that the standard deviation for the sample is equal to the standard deviation for the population divided by the square root of n. And this as long as we have no more than 10% of the population being sampled as independent. All right, so let's look at the females. There's a normal distribution because population was already normal. The mean for the sample of the females should be the same thing as the mean for all the females, which is about 56.4. The standard deviation for the sample should be the standard deviation for the whole population of females divided by the square root of all the females taken. So it should be 2.7 divided by the square root of 12, which is about 7.8. With males, it's also normal because population is normal. The mean for the sample, same thing as the mean for the whole population, 55.7. Standard deviation for the sample is the same thing as standard deviation for the population divided by the square root of the total number sampled. So 3.8 divided by the square root of 8 is 1.34. Because there's more than 80 10-year-olds in the world or in the United States, we know this is less than 10% of the population. And there's more than 120 teenage girls in the United States, so that's also less than 10% of the population. We've also already know that we're subtracting, again, the difference between two standard deviations, as in standard deviation of females, subtract the standard deviation of the males. We should use this formula where we combine the two standard deviations and just square root the sum of those. And it comes out to be this: standard deviation 1 squared over n, standard deviation 2 squared over n, because remember you squared the whole thing. And because you squared it in the original formula said this: standard deviation squared plus standard deviation squared. Since you square them, it got rid of the square root symbol, but it squared the numerator. Hope that makes sense. It should make sense. So we did the math for it. Standard deviation of the female squared over the number of females plus standard deviation of the male squared over the number of males should be 2.7 squared over 12 plus 3.8 squared over 8, which gives you the difference of that. So that standard deviation is about 1.55. This is similar to the result you would have found if we did a simulation. All right, so these are the rules we need to follow. You got to take a simple random sample from both populations. The shape, when the population, the distribution is normal, the sample distribution of X bar minus X bar should also be normal. In other cases, sample distribution of X bar minus X bar would be approximately normal if the sample size is large enough, n greater than 30, and so forth. We don't have to check for normality. The center should be the same thing as subtracting the means for the center. And standard deviation is written by this formula, as long as we have 10% of the population. Here's another example: medium or large soft drinks. We're going to describe the sample distribution here. A fast food restaurant uses an automated filling machine to pour in its soft drinks. The machine has different settings for small, medium, and large soft drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid ale dispensed by the machine is normally distributed with a mean of 27 ounces and a standard deviation of 8 ounces. When the medium setting is chosen, the amount of liquid M for medium dispensed is normally distributed with a mean of 17 ounces and a standard deviation of 0.5 ounces. The test manufacturers claim the restaurant manager measured the amount of liquid in each of the 20 cups filled with large setting and 25 cups filled with a medium setting. Let X bar sub 1 L and let subtract X bar sub M be the difference between those two means. So the problem says, what is the shape of the distribution and why? Since they both came from normal distributed, the shape should be normal. And that's the reason why, because they both came from a normal distribution already. Even though they didn't have 20 more than 30 of the cups, it came from normal distribution. Find the mean of the sample distribution. All right, so we want to find the mean from both of those. Basically, I'm going to take the mean for the first set. There's actually a population he actually gave us. So I'm going to take the mean of the first set, take away the mean of the second set. And the mean of the second set was 17. The mean of the first set was 27. So 27 take away 17. So that difference should be 10 ounces. Find the standard deviation for the sample. Well, standard deviation for the large minus small, large minus medium, should be the square root of the standard deviation, what we know about the population. So the first one was 0.8, and it's going to be squared, and the second was 0.5, and it's going to be squared, divided by the total number of each. So the first one had 20, and the second one had 25. And if we do the math for it, you should get it to be 0.205 ounces as your standard deviation there. And then the last one says, well, that's it. So we found the standard deviation and we found the mean for both of those situations. Note that we do not need to check a 10% condition because we're not sampling without replacement from a finite population. All right, let's actually get to a two-sample t-statistic. These are the formulas I already know. We're using that for the difference, for the standard deviation. We got the difference of two samples. If we was looking at z-score, it would be the value, take away the mean, all over the standard deviation. In this case, that value is the difference of two means. Subtract the difference of two population means, divide by standard deviation using this formula. It's unlikely that we'll know both standard deviations. All right, standard error. Standard error is still part of the margin of error formula. So it's basically going to be the z-score divided by the standard error, or z-star divided by the standard error. So it's written by this formula. For a two-sample t-statistic, we have a t-score being the exact same thing. Notice how this is all the same information for our t-score. T-star. So even though the t-score and the z-score, the t-distribution is slightly different than the z-distribution, it's still going to be pretty accurate by using a t-distribution. All these rules still apply. Random, 10%, large enough sample being greater than 30. Has to be normal though. So if the sample is not normal, you can't actually use the t-distribution for it. So it has to be a normal distribution or come from a normal distribution or it being greater than 30. So option one, we have this degree of freedom. And here's a degree of freedom if you're going to use technology. It's going to give you a decimal value, but this is the form you're going to use for degree of freedom. If we're going to use our calculator to do it, we'll do that today as well. The conservative way, our degree of freedom is still just n minus 1. So you got 2 degrees of freedom. You got degrees of freedom with the first number, and you got a degree of freedom for the second n. Always take the smaller of the two. We'll talk about the rest of this in class. That's all I have for now.